Hello and welcome to today's lecture on unguided media. On completion of this lecture, the students will be able to explain propagation methods in wireless communication system, broadcast radio communication, terrestrial microwave communication, satellite microwave communication, infrared communication, and also we shall compare these wireless communication techniques. Here is the outline of this lecture. I shall give a brief introduction about this lecture, why this wireless communication is so important in the context of data communication systems. Then we shall discuss about spectrum of wireless communication, various frequency spectrums that are used for wireless communication, then wireless communication configurations, various configurations which are used for wireless communication, I shall discuss briefly. Then various propagation methods we shall discuss, such as broadcast radio. In the context of wireless communication we shall discuss. Then we shall discuss broadcast radio, terrestrial microwave and satellite microwave, and finally the infrared communication. So essentially we shall be covering these 4 wireless communication techniques, such as broadcast radio, terrestrial microwave, satellite microwave and infrared communication. As I mentioned in the earlier lecture, the communication media provides the physical path between transmitter and receiver in the data communication system. As you know, it can be divided into 2 broad types: guided transmission media and unguided media. And in the last lecture we have discussed in detail the various guided communication media, such as twisted pair of cable, coaxial cable and fiber optic cable. Now in case of unguided media, as I mentioned, it provides a means for transmitting electromagnetic signals through air but do not guide them, so we may call it wireless communication. Question naturally arises, why wireless communication is so important? As you know, with the proliferation of portable mobile equipments such as laptops, palm tops, cell phones, PDAs and so on, what is happening, people are carrying various electronic equipment with them. As a consequence, what they want to communicate from anywhere to any place, anywhere from any location, and they want to communicate. How that is feasible? That cannot be supported by guided or wired communication media. So anywhere, anytime communication is feasible only by wireless communication, and that is the topic of today's lecture. Broadly, as you can see, the electromagnetic spectrum used for wireless communication is divided into 3 parts: the radio wave and microwave. Again, this can be divided into 2 parts: radio communication and microwave communication, as we shall see. Then there is infrared and then light wave. So this wireless communication is possible in these 3 ranges. Now in case of wireless communication, as I mentioned in the last lecture, communication is dependent on the antenna. Antenna plays a big role in the wireless communication. The characteristics of the antenna: and the frequency spectrum that it transmits in the air will play the important role, or in other words, it will decide the quality of transmission, the bandwidth of signal, and various other things. So, for transmission, what we require? An antenna that radiates electromagnetic radiation in the air, and for reception we also require another antenna that will pick up electromagnetic waves from the surrounding media. So, it is somewhat like this. You have got an antenna which is transmitter, and here you have got another antenna. So, this is your transmitter and this is your receiver. So, electromagnetic signal is passing, will go from one to another through this antenna. And in this case, as I mentioned, antenna will play a very important role, a key role, as we shall see. Basically, there are two types of wireless communication. One is your in one case it is called point-to-point communication. In this case, transmitting antenna puts out a focused electromagnetic beam in a particular direction. So, the antenna will focus a signal in a particular direction, and in that case the transmitter and receiver must carefully align, and obviously this will allow point-to-point communication. So, in this configuration you have got two antennas which are communicating with each other. So, it is a point-to-point communication. This is one possible configuration. Second possible configuration is the transmitted signal spreads out in all direction. So, in such a situation, whenever the signal spreads out in all possible direction, the signal can be picked up by many receivers with the help of antennas. So, the signal can be received by many antennas. So, this is called broadcast communication. So, as we shall see, we have got two basic configurations, point to point and broadcast. So, there are various ways of doing it, as we shall see. Now, let us discuss the various propagation methods, the methods by which communication takes place in the air. First one is known as ground propagation. Ground propagation will take place below 2 megahertz. So, we have seen that this ground propagation is possible below 2 megahertz, and in this particular case the communication takes place with the help of ground signals. Before that, let me explain the overall situations. Suppose this is our earth, then you have got air, then there is an ionosphere. Why it is called ionosphere? Because in that upper layer of the atmosphere, the air is in charged condition, that means ionized condition. There are positive and negative particles, that is why that is called ionosphere. So, you have got earth, then I have shown an antenna, and here is the ionosphere. So, ionosphere will play an important role in some cases, as we shall see, but let us see what happens in case of ground propagation. In case of ground propagation, as you can see, ionosphere does not play any role. So, what is happening here? The signal is propagating in all directions, and the signal is hugging the earth. So, the signal is propagating by hugging the earth. So, around the ground the signal is going on. As a result, with along the ground it can propagate over long distances. One typical example is AM radio, which we listen that we listen Calcutta A, Calcutta B, and so on. That AM radio is the example of this ground propagated signal. Now, this is the first mode of communication. Second mode of communication is known as sky propagation. This sky propagation is possible for frequency range from 2 to 30 megahertz. 2 to 30 megahertz of signal can propagate through air and in this case the mode of propagation is known as sky propagation. Why it is called sky propagation? In this scale, as we shall see, the electromagnetic signal which will come out from the transmitter will go to the ionosphere layer, then it will bounce back. Let us see how it happens. So as you can see, the wave signal is propagating, and it is reflected back by the ionosphere, and it is receiving the antenna. So in this way, as you can see here, so the signal gets reflected by the ionosphere and comes back to the receiving antenna. So in this case, the ionosphere plays a very important role, because as you know, ionosphere is at a much upper layer of the atmosphere, and with the help of this sky propagation, the signals can be sent over a very long distance. For example, we hear Voice of America, radio picking, and various shortwave signals that comes through sky propagation. And the citizens band radio falls in this range. So sky propagation is very useful for long distance communication and with the help of the ionosphere. Then the third mode of communication, as I mentioned, a line of sight communication, that is above 30 megahertz. Above 30 megahertz, the signal behaves like somewhat light. Frequency is very high, wavelength is small. So here in this case it has to be point-to-point communication. The signal gets obstructed if there is building, if there is some artificial or natural structure, signal will get obstructed. So in such a case, you must have line of sight propagation, and as you can see how it happens. So you see you have got two antennas, both are communicating with each other with the help of line of sight communications. So in this case, the requirement is that the antenna must be relatively quite high so that the line of sight communication is feasible. And as you know that FM radio, television signals, cellular phone, terrestrial microwave, satellite microwave, all these uses this line of sight communication. So the previous two, that means sky propagation and ground propagation, these are essentially broadcast communication. On the other hand, this line of sight communication which takes place for frequencies above 30 megahertz is line of sight communication. Now the wireless transmission techniques can be broadly divided into three types, as I mentioned earlier. What are the three types? First one is radio wave, second one is microwave, last one is infrared. So first one is in the radio frequency range, second one is the microwave range, and in the this is essentially light, very high frequency range, that is infrared, as you have seen in the that wavelength, that frequency spectrum. So these are the three broad wireless communication techniques that we shall discuss. First, let us consider the broadcast radio. As I mentioned, the broadcast radio operates in this range 30 megahertz to 1 gigahertz. 30 megahertz to 1 gigahertz, and in this case the communication is omnidirectional in nature. Omnidirectional in nature means it propagates in all directions from the antenna. As you can see here, the signal is propagating just like a wave in all directions from the antenna. Just like if you throw a stone in the pond, the waves propagate in all directions with that as the center point. Similarly, here the antenna is the center point. With that antenna as the center point, wave is propagating in all possible directions, as you can see here. So this is called this wave propagation is omnidirectional in nature, it propagates in all directions. But here the communication has to be line of sight. This is a very important characteristic in this case. The signal gets obstructed by building, by other structures. So it has to be line of sight communication. And as a consequence, the distance that it can communicate, distance that can be covered is given by this relation 7.14 root kh. So 7.14 root kh. This is the equation that is used for maximum distance, where h is the height of the antenna. So h is essentially height of the antenna. Height of the antenna. And this k is a correction factor that is equal to 4/3. That means there is some bending of the signal, electromagnetic signal, as it goes from the transmitter to the receiver. As a result, it covers little more than what is possible by line of sight communication. So that factor is taken care of by k, and as you can see here, the distance that it can cover is 7.14. So that's why what you normally do, as you can see in this particular case, we have put the antenna height quite high. So we had usually there is a tower on which the transmitted antenna is installed, or that antenna is on the top of a roof, or antenna is on the top of a building, or sometimes on the top of some mountain. So to cover larger area, usually the height is made, the antenna is placed on some high, that height of the antenna is made higher, so that it can reach longer distance. And in this frequency range, 30 megahertz to 1 gigahertz, it can penetrate valve. That is one advantage as well as disadvantage. What is the advantage? The advantage is that this type of signal you can receive inside your room. The antenna can be inside the house, inside the room. So signal can penetrate the wall and can reach you. So that way it is advantageous. Disadvantageous is there is no privacy. That means the signal can be received, since it is a broadcast signal, can be received by many people. So if you want to send some private signal which should not be communicated to others, you cannot do that. However, you can do that by using encryption, that we shall discuss later. And for this type of signals, the ionosphere is transparent. What do you mean by that? So for this kind of communication, the signal passes through the ionosphere. It does not get reflected by the ionosphere. So the problem of multipath communication does not exist. In other words, there is, multipath communications leads to many problems. What are the problems that can arise? Because of that, you can have some kind of fading, which you must have observed in case of shortwave radio. Whenever you listen to some shortwave radio, which comes via sky propagation, not in this range. So in such a case, what happens? There is fading, and so in this particular case, there is no problem of fading, and multipath propagation does not take place. You receive signal directly from the transmitter to the receiver. That is an advantage in this particular frequency range, 30 megahertz to 1 gigahertz. However, here the attenuation is dependent on two parameters, and it is given by this relationship 10 log 4 pi d by lambda square. So as you can see here, d is the distance. The attenuation increases at the rate of d squares. As the distance increases, the attenuation increases significantly. That's why longer the distance, weaker the signal. That happens. And moreover, the attenuation is inversely proportional to the square of the wavelength. That means higher frequencies are attenuated more than the lower frequencies. So this is another characteristics of this frequency range. And this type of signals are less sensitive to rainfall. And as I mentioned, signal can travel long distances, and multipath interference does not exist. in this particular case. So these are the several parameters or characteristics of broadcast radio. And these are the typical applications of broadcast radio: FM radio, then television, then data networking. These are the typical applications of broadcast radio. Microwaves. So then comes the after that the broadcast radio communication comes the microwave frequency. Microwave frequency lies in the range 2 to 40 gigahertz. So in this case 2 to 40 gigahertz it is quite high frequency, and in this case it is possible to have very highly directional beams. That means you can send highly directional beam from the transmitter towards the towards the receiver, and you can have point to point communication, and that's why it is very suitable for point to point and satellite transmission. And for that purpose usually we use two different types of antennas. As you can see here, this antenna is known as horn antenna. This is known as horn antenna. So here the signal comes and then it gets reflected by this particular shape of the antenna, then it goes in all the rays goes in a particular direction. So there is some kind of parallel beams of light goes in a particular direction. So from the transmitter it comes here to the antenna, then it gets reflected in this way, then it reaches another type of antenna which is known as this type of antenna. This is known as this type of antenna, DISC. So this type of antenna, and this is horn type of antenna. So here you can see the horn type of antenna receives the parallel signals, then it focuses it at a particular point, and at this point some sensor is kept, and then this signal is taken to the amplifier for amplification and other thing. So both these antennas are fixed rigidly because here it has to be point to point communication. So the antenna must be placed very rigidly in one place like this. This is another antenna placed very rigidly in one place with the help of some structure. Then you can have point to point communication between these two antennas. So it can focus a narrow beam to achieve line of sight communication, as I mentioned, with the help of these two types of antennas. This microwave communication has got two varieties. First one is terrestrial microwave. In case of terrestrial microwave, it is used for long haul communication, and usually it uses this 4/6 gigahertz band. Obviously, since the frequency is in the lower end, it requires bigger antenna, 10 meter or more diameter, and it is used for primarily used for long haul communication. Long haul communication means whenever you have to transmit signal over a long distance, what can be done? Say this is, let's assume this is the surface of the earth. Then you can erect antenna like this, so it will transmit in this direction. Then you can place another antenna here, it will receive from this, so it will go here. Then after receiving it, it will do the amplification and transmit to another antenna. So in this way a cascade of antenna can be used one after the other to send signal over a long distance. So not only this type of communication is possible by this, you can have point to point link between buildings. In this particular case you can use higher frequency, so that antenna size is small, 20 gigahertz antenna will be smaller in size and cheaper in cost. And this terrestrial microwave can be used as an alternative to coaxial cable and optical fiber. As you know, coaxial cable and optical fiber is also used for long haul communication in telephony. instead of using the coaxial cable and optical fiber, one can use terrestrial microwave. But in this case, as I mentioned, the antenna has to be properly placed, and then the height should be proper and distance should be adjusted so that the signal reaches the antenna, and the signal is amplified and then retransmitted. So essentially they are acting as repeaters. So these are acting as repeaters. And as I mentioned, in this case also the formula of maximum distance d is equal to 7.14 root kh is applicable. Here d is the distance in kilometer and h is the antenna height in meters. And as I mentioned, the value of k is an adjustment factor because it is not fully line of sight, the signal gets bent, and the adjustment factor is 4/3, that is 1.33. Let's assume the antenna height h is equal to 100 meter. So if you substitute this here and taking the value of k is equal to 4/3, then you will find the distance is roughly equal to 82. So sorry, say 80. This is 100 meter. So it will be roughly equal to 82 kilometer. So with an antenna height of 100 meter, you can have the distance that can be covered is 82 kilometers. So here the antenna height is in meters and distance is kilometers. So with an antenna height of 100 meter, you can cover a distance of 82 kilometers. That's why you will find that we will be finding repeaters about at the range of 60 to 80 or 100 kilometer distance, because antenna height is typically around 100 meter. For example, if you come from Calcutta to Kharagpur near Paspura, which is midway, that means around 60 kilometer, you will find there is microwave towers which are acting as repeaters between the signals coming from Calcutta to Kharagpur or Kharagpur to Calcutta. So this is the distance and height relationship. Then comes the transmission characteristics, that is the attenuation. So as I mentioned, here also the attenuation characteristic is 10 log 4 pi d by lambda square. That means the attenuation is proportional to distance square and inversely proportional to wavelength, or attenuation is proportional to frequency. That means higher frequency signals are attenuated more. However, higher frequency signals provide more bandwidth. That means we prefer to use higher frequency bandwidth, higher frequency for communication, because it gives you higher bandwidth, but higher frequency gives you more attenuation. So it's some kind of trade-off, and we have to choose suitably. You have to judiciously select the frequency so that you don't have much of attenuation. At the same time, you can get reasonably good bandwidth. For microwave signals, attenuation increases with rainfall. This is a very important factor. That means these signals, the frequencies within this range, are affected severely by rainfall. Apart from distance, apart from frequency, you can see rainfall plays a very important role in attenuation. So that means when the weather is bad, in the rainy conditions, the signal will be poorer, and that is the reason why the error occurs, more error occurs during rainy seasons. The signal to noise ratio degrades. As a result, more error occurs in the signal. Now we have discussed the terrestrial communication. Now comes the satellite microwave communication. We have seen that in the previous slide that distance d is proportional to 7.14 root kh. That means if we can make the height very high, we can cover a very large distance. So why not put an antenna in the sky? That is the basic idea of basic idea of satellite microwave. So in satellite microwave, what we are trying to do, we are trying to put a relay station in the sky at a very large distance. So in this case, as we shall see, the antenna height is quite large. For example, it can be as high as 36,000 kilometers. So as we shall see later, this will allow to cover a very large distance. And here with the help of this microwave, we can use you can link 2 or more earth stations. There can be 2 earth stations, and essentially that antenna in the sky satellite will be acting as relay station. So with the help of this relay station, 2 ground stations can communicate with each other, 2 or more ground stations, as you shall see, because we can have 2 different modes of communication. Again, it can be point to point or broadcast. Let us see the configurations. So in this particular case, as you can see, it is a point to point communications. Here we have got the satellite in the sky, and here you have got the 2 ground stations. This is one ground station, this is another ground stations. So here there is a point to point link, and here the signal is going from this ground station to the satellite. Here it is received and then amplified and returned back to the station. So signal from here also goes to the satellite. Here it is received, then amplified, and then it is returned back to this ground station. So this way it can cover a very long distance. And this is the second alternative, where it can be you can achieve broadcast with the help of satellite microwave. So you see here you have got the satellite, and it can cover a quite large area which is in the footprint. It is called the footprint of the satellite. All the ground stations which is under the satellite in the footprint of the satellite can receive signal from here. So here you have got one transmitter. From this transmitter, signal goes to the satellite, then it is transmitting to a number of stations, and it is broadcasting that signal to a number of other stations. So you can see here this is broadcast link via satellite microwave communication. Now question arises, where do we put the antenna in the sky? There are 2 alternatives. One alternative is the satellites can be about say 800 meter above the earth. That is one possibility, not very high. Then a large number of satellites can rotate, and with the help of that communication can be done. But it has been found that the most conventional way, or rather more popular way, is geostationary orbit. In this case, the advantage is, let us go back to the previous diagram. What we want, the satellite should remain stationary with respect to the sky, with respect to the earth. That means if this is the earth, and here there is a ground station, and here is another ground station, they want to communicate with the help of the satellite. So here you have got the satellite, and if the communication has to be reliable and steady, it is essential that this satellite remains stationary with respect to the earth. How that can be achieved? That can be achieved by placing the satellite in a geostationary orbit, and the distance is about 35,784 kilometers. So this height is quite large. That means 33,578 kilometers, quite large distance. So at this height we have put the antenna, and it remains stationary because it is placed in geostationary orbit. So relative position of this ground station with respect to the satellite does not change. What are the advantages of this? One big advantage is the satellite can cover a very large distance because the antenna height is very large, and it can be shown that with the help of 3 antennas the entire globe can be covered. For example, here you have got your Earth. So one satellite here, one satellite here, 120 degree apart another satellite, and here another satellite. So with the help of these 3 satellites one can cover the entire Earth. So entire globe can be covered with the help of 3 satellites, and so this is a big advantage. The height is utilized, and you can see to communicate any ground station on the Earth only 3 satellites is sufficient. So this is one very big advantage. However, now there is competition to put satellites in the sky. All the countries are competing with each other to put a satellite of their own in the sky, and that has created a problem. And particularly we cannot have many satellites. There is some restriction. For example, there should be you have got only 360 degrees. So when you have got 360 degrees in the geostationary orbit, then minimum 4 degree spacing is required if you use 4/6 gigahertz band, and minimum of 3 degree spacing is required if you use 12/14 gigahertz band. As we shall see, these are the popular frequency bands used for microwave communication. So the number of satellites is restricted because of these minimum spacing required, so that there is no interference between the signals of generated by 2 satellites, because they are using this common frequency bands, 4/6 gigahertz frequency band or 12/14 gigahertz frequency band. Then another very important characteristic is that you can have a number of transponders, and a single orbiting satellite operate on a number of frequency band called transponders. That means a single satellite can operate on a number of frequency bands within that 4/6 gigahertz frequency band, and with the help of a number of transponders the communication with many ground stations is possible. Moreover, the satellite receives transmission on one frequency band, amplifies and repeats the signal, and transmits it on another frequency band. So you have got 2 frequencies, as you can see. One is known as uplink frequency, another is downlink frequency. So here is your ground station, and here is your, that means here is your satellite, and here is your ground station. These 2 can communicate with the help of 2 frequencies. One is your uplink frequency, and another is your downlink frequency. You have to use 2 separate frequencies so that there is no interference, and two-way communication is possible. And here are the common frequency bands used. As you can see, C band, 4/6 gigahertz band, and here the downlink frequency range is 3.6 to 4.2 gigahertz. Then uplink frequency band is 5.925 to 6.425 gigahertz. So this is downlink frequency band, and this is the uplink frequency band. Similarly, for Q band, this is 12/14 gigahertz band, and as you can see here, the downlink frequency is 11.7 to 12.2 gigahertz, and uplink frequency is from 14.0 to 14.5 gigahertz. Similarly, there is another frequency band that is known as Ka frequency band, which is in the range of 18/28 gigahertz. The downlink frequency is 17.7 to 21 gigahertz, and uplink frequency is 27.5 to 31.0. one point you must notice that downlink frequency band is lower, and here we are using higher frequencies, uplink frequency is higher. What is the reason? One possible reason for that is, as you know, higher frequencies are attenuated more, because the attenuation is proportional to frequency square, or 1 by lambda square. So since the satellites are powered by solar cells, there is a constraint on the availability of power. So the satellites could not put high power. On the other hand, ground station can put much higher power in the antenna. So uplink frequencies with higher frequency bands can drive with higher power, so it can sustain higher attenuation. On the other hand, downlink frequencies which are transmitted by satellites which are powered by solar cells cannot have very high power, so they choose lower frequencies, so that attenuation is lesser for downlink signals than the uplink signals. So here it is uplink signals, it is compensated by higher power of the ground stations. Then there is another very important innovation is very small aperture terminal. It is a very low cost solution. Here, as you can see, a number of subscriber stations are equipped with low VSAT antennas, particularly whenever communication has to be established among a number of geographically dispersed stations. Then this is a very convenient technique of achieving it. Here what can be done, using some protocol, these stations can share a satellite channel for transmission to a hub station. This is a hub based. There will be a central station called hub station, and the hub station can exchange messages with each of the subscriber as well as relay messages between the subscribers. So we can see here this VSAT is a very low cost alternative to have communication among a number of stations, and let us see how this is done. This is the typical VSAT configuration, and this is the hub. Here you have got the hub, and these are the ground stations. Here, as you can see, the size of these antennas is small. That's why the name has come. VSAT stands for very small aperture terminal. By very small aperture, really mean the diameter of these antennas will be quite small compared to the hub, and hub the diameter can be around say 10 meter. On the other hand, these VSAT terminals can have much smaller diameter, around say 1 meter or little more than a meter in diameter. It depends on the frequency band that is being used. For Q band satellite, it can be it might be around 1 meter or even lower. So you can see here how the communication is taking place. So each of these VSAT antennas can send signal, as you can see 1, 2, 3. So n such stations can send, and as you can see they are going to the in some time division multiplex form that will go to the hub. Then the signal coming from the hub is broadcasted by this satellite, and it goes to all the other stations. That means here you have got a number of other stations, slave stations you can say, they will be receiving this signal. So here you can see the 25, each is sending at the rate of 56 kilobits per second. So this 56 kilobits, these are all time shared and reaching the hub. On the other hand, 256 kilobits per second data rate is coming from the hub to the satellite, then it is broadcasted to all the VSAT receivers here. Now, what are the advantages of this satellite communication? One advantage is wide geographic area. As I have mentioned, you can cover a very large area. For example, with the help of 3 satellites, you can cover the entire globe. Another very important advantage is independence from terrestrial communication infrastructure. You know, whenever you want to have wired infrastructure, you have to first lay the cable. For example, in our country recently, there was deployment of optical fiber cable by Reliance and various other groups. So we have seen that cable laying is really very complex and tedious process. So that is not required, and that kind of infrastructure is not required. You simply put an antenna, VSAT antenna, and do the communication. It can be anywhere. And because of this, it has got very high availability. Particularly in wired configuration, we have seen that there may be many problems because it is relayed through a number of stations, but it is essentially direct, and only link is the satellite. And as a consequence, the availability of satellite microwave communication is very high. And another important feature is communication costs are independent of the transmission distance. We have seen whenever it is a wired communication, even for our telephone calls, depending on the distance, the charge varies. For example, if you want to make a call from Kharagpur to Calcutta, the charge is much less than if you want to make a call from, say, Kharagpur to Bombay, because of the higher distance. That means STD rates varies with the distance. But here that is not so. Here the communication costs are independent of the transmission distance. You can cover from any point to any point in the country, or any point to any point in the other part of the globe, and the cost of communication is same. And it is a very flexible network configuration. Why flexible? It can be very easily scaled up. The number of stations that can be communicating with each other can be increased very easily and in a flexible manner. And because you don't have to deploy anything but the antennas at different locations. So this allows you rapid network deployment. And another very important advantage is centralized control and monitoring, because by monitoring you have got a central hub. By monitoring and controlling that, you have a very good control. That's why the centralized control and monitoring is feasible in this particular technology. And as a consequence, this satellite microwave communication is becoming very popular, and it is finding use in various areas. I have listed only a very limited number of applications, but the application domain is very high and it is numerous. For example, it is used for television distribution. We are familiar with the LPTs, low power transmitters, and high power transmitters that are being used. And actually, the low power transmitters and high power transmitters are receiving the satellite signals from the studio with the help of the satellite signals. And it is also used for long distance telephone transmission. Long distance telephone transmission is possible with the help of this satellite communication. As we have seen, you can put repeaters at a distance of about 60 to 80 kilometers, and you can achieve that sending trunk signals with the help of this VSAT instead of terrestrial. You can use either terrestrial microwave or you can use VSAT satellite. And you can set up a private business network using VSAT. For example, an organization can have offices in different parts of the country. They want to communicate with each other. So they can have VSAT antennas at various places and a hub in one place. So that will allow them to have private business network, or they can set up an intranet where the LANs of an organization in different places can be linked with the help of VSAT antennas to set up an intranet, which we shall discuss in more detail later. And many other applications like video conferencing, in-house training, this can be done with the help of these satellite microwave communication. These are some of the important areas where it is being used. NICNet, for example, this is National Informatics Center. Informatic Center, they are having VSAT antennas in all district headquarters with their hub, central hub in Delhi. So now they collect all the data with the help of VSAT antennas. So that is called the NICNet, and that is one very important area. For example, another project is Educational Research Network. This Educational Research Network was also set up with the help of VSAT antennas, and by using this satellite microwave network. Nowadays, you will find advertisement in TV for DD Direct. That means in your home you can receive television signals by a very small antenna and a small box, a set-top box. So that is also possible with the help of these DD Direct, satellite microwave signals. And the NPTEL project for which this lecture is getting recorded, that will also transmit signals to various colleges in the country with the help of satellite antenna, satellite microwave system. However, this has got a number of disadvantages. One very important disadvantage is long propagation delay. In case of satellite, as we have seen, the antenna is located at a distance of 36,000 kilometers away from Earth. The signal has to travel 36,000 kilometers, and it has to return back to the receiver, another 36,000 kilometers. So this round trip delay is about 1/4 of a second. That poses a problem, and particularly to identify whether two stations are sending together. That means collision detection is difficult. So that has to be taken care of. Then this is another disadvantage is it is inherently a broadcast facility. So since it is inherently a broadcast facility, the antenna transmits something and a number of receivers are listening to it. So it is difficult to transmit private data. However, this can be taken care of by suitable encryption technique. So new techniques are emerging with the help of which the security can be achieved, that we shall discuss later. Finally, because of it is passing through the medium, and there are various problems. You have to perform error control. The data can get corrupted, and sometimes we face the problem of slow and fast communication, which is flow control. So we have to perform error control or flow control for reliable communication. So we shall discuss about these two issues, error control or flow control, later on. Finally comes the infrared communication in the range of 0.3 to 200 terahertz. It is very useful for point-to-point and multi-point applications within confined areas such as a single room. Here it uses transceivers that modulates non-coherent infrared light. In this case also, since it is light, it has to be line of sight either directly or via reflection from the light colored surface or wall, ceiling of a room. One advantage is, in this case, the signal does not penetrate walls, so secrecy can be very easily maintained. Another very important advantage is the frequency allocation. There is no frequency allocation issue, so there is no licensing required. Particularly in this context, a IRDA is playing a very important role. IRDA stands for Infrared Data Association. This is a consortium of 150 companies to maintain and develop standard. So IRDA has developed some standard with the help of which the communication can be performed over very short distance. So the objective is to have device to device seamless communication over a short distance, typically 1 meter. So particularly we have found that nowadays if you want to connect your laptop to a computer, you have to use a cable, or if you want to connect a printer to a laptop, you have to use a cable. So that can be avoided with the help of this IRDA communication, infrared communication. Here there is no need for cable. Sometimes cable poses a problem. However, the data rates are not very high. Initially it was 2400 bits per second to 115.2 kilobits per second, and it has now been extended to 1.15 to 4 megabits per second. And a layered protocol has been developed. Here is the physical layer, IR-PHY, and this is the data link layer having 3 components, HLDC, IR-LAP and IR-LMP. These layered architecture has been protocol layer has been developed by the IRDA, Infrared Data Association. For example, here you have got a transmitter. It can transmit over a angle of say 15 to 30 degree, and here is a receiver. It can receive with an angle of say 15 degree. So and the communicate can be done with the help of 1 meter. So this is the IRDA standard that has been developed for infrared communication. So with this we come to our conclusion on this data communication by using wireless communication. Here are the review questions. Question number 1 is, on what parameters the quality of transmission depends in case of transmission through unguided media? What are the factors responsible for attenuation in case of terrestrial microwave communication? What parameters decide the spacing of repeaters in case of terrestrial microwave communication? Fourth question is, why 2 separate frequencies are used for uplink and downlink transmission in case of satellite communication? Fifth question is, why uplink frequencies are higher than downlink frequencies in case of satellite communication? So these questions will be answered in the next lecture. Here are the answer to the questions of lecture number 5. Question number 1 was, on what parameters the quality of transmission depends in case of guided transmission media? Answer is, as I have discussed, it is mainly decided by the frequency of transmission and the characteristics of the medium, transmission media. That happens in case of guided media. Why wires are twisted in case of twisted pair of transmission media? That was the second question. As I have discussed in the last lecture, it minimizes electromagnetic interference between the pairs of wires which are bundled together so that the crosstalk is minimum. Third question was, give a popular example where coaxial cables are used for broadband signaling. One popular use is cable TV, you are familiar with. That is where it is used. Fourth question was, find out the critical angle for a step indexed optical fiber for N1 and W is equal to 0.04. So N1 was 1.48 given. So here the calculation has been given, and as you can see here, you can find out the angle which is roughly equal to 82 degree for these parameters. So it can be very easily found because the angle of refraction is 90 degree. So from that you can very easily calculate it. And as you can see here, the angle of reflection incidence has to be more than 82 degrees so that you have got reflection. Other signals will pass out through the cladding material. So here is the last answer of the last question. In what way multi-mode and single mode fibers differ? Essentially it is the diameter, cord diameter, that is the difference here, and the cladding diameter, and repeater spacing is 2 kilometer for multi-mode fiber, and for single mode fiber, as you can see here, the core diameter is 8 to 12 micron, cladding diameter is 128 micron, and the repeater spacing is 20 kilometer. So with this we come to the end of this lecture. Thank you.